So of course in 1957, Sputnik was launched, and that opened a new era in the space race and beginning to think about how space can be used to help us do the things that we do on Earth. And today there are thousands of man-made satellites now in orbit. And in fact, over the next few years, we expect tens of thousands more will be launched. They provide crucial services and help address fundamental challenges. We rely on them for precision weather forecasts, helping us to avoid deadly storms. Satellite image in various bands, allowing us to do remote sensing for agriculture and environmental monitoring for weather-dependent industries. And it's amazing that satellites can even see through clouds. And of course, finally, GPS satellites that make location services available nearly everywhere in the globe. But we still have a lot to do. We've only scratched the surface of what satellites can do. We can provide Earth observations in near real time with details that were previously impossible. Cloud, edge, AI, and the Internet of Things technologies are driving new breakthroughs, providing that ubiquitous internet with higher throughput and lower latencies. So our next speaker is Ranveer Chandra, Managing Director of Research for Industries at Microsoft. He's going to show us what lies ahead for this emerging field. We'll also get to look at the technologies in action with demos presented by some of his colleagues from Microsoft Research. So with that, I will say over to you, Ranveer.
Hi, welcome to the talk. I am Ranveer Chandra. I manage networking research at Microsoft Research in Redmond. And today I am here to talk about an exciting new project in my team on enabling real-time insights of events happening anywhere in the world. This is a cross-group effort with several researchers across different labs, many of them in Microsoft Research in Redmond. Also, this is work with product teams, with interns, and with academia. So there are several types of Earth observations and several reasons why Earth observation is important. For example, you can use it to monitor farms, to monitor crop stress, to monitor water levels. It can also be used to track ships, maritime and smuggling, as well as supply chain events happening across the world. Similarly, if you could monitor the Earth, you could monitor things like disasters. Where are the floods happening? For example, right now in Pakistan, or wildfires happening anywhere. If you could monitor all of these events, you could get real-time insights of what's happening where, not just knowing how things are happening, but also react to these events worldwide. One of the ways you can get these real-time insights is through Earth observation. That is, you could have these sensors in different parts of the world. You could connect them using cellular, but 80% of the world's surface doesn't have terrestrial internet access, for which you would need satellite connectivity. You could get data from sensors, from cameras that are connected to satellites and that come down to the ground, providing you information from all over the world. It is not just about IoT. The other type of sensing is what is known as remote sensing. You could have these satellites equipped with cameras, not just optical, but maybe hyperspectral cameras that could be streaming information, taking images from different parts of the world and streaming them down to the Earth. That is, you could be seeing how the forests are doing, how the water is doing, how the farms are doing in different parts of the world without having sensors at that locations. When we say Earth observation today, we are referring to both, either using remote sensing, using satellites, or using IoT devices, these Internet of Things devices that are connected either using satellites or using any other method as well. So over the last few years, there's been a significant proliferation in the number of low Earth orbit satellites. These low Earth orbit satellites are very low cost, much lower cost. And it's also much easier to launch them. Think of like a ride sharing through which you can pool your satellites with other satellites and send it over to space. So earlier, what would cost, say, maybe $1 million or more to launch a satellite, now it just costs maybe, say, $100,000, which makes it really inexpensive for many companies, many organizations worldwide to launch satellites in outer space. These satellites, be it these low Earth orbit satellites, go around a few hundred kilometers around the Earth, and this is the pattern that they take around the Earth. Every 90 minutes, they would go and circle back. And with this, if they have a camera, they could be imaging every, say, 90 minutes. They could have a revisit interval. Or if it's an IoT satellite receiver, they could be going back every 90 minutes to the same point over the Earth. These Earth observation satellites have low orbits. That is, as I said, they go only a few hundred kilometers above over the Earth. And because of that, they can get images at very high resolution. Also, because they are so low, so close to ground, you could connect sensors on the ground directly to these low Earth orbit satellites. Further, because launching these satellites is inexpensive, instead of having just one or two satellites, you could have large constellations, a few hundred of these satellites, maybe even 1,000. The benefit is that you could have very frequent intervals. You could have a satellite over any point in Earth at any instant in time. Further, as the hardware is improving, you're seeing these low Earth orbit satellites carry not just regular optical cameras, they carry multispectral, in some cases even hyperspectral cameras aboard these satellites. These satellites also have compute in them, enabling edge compute. You could be running part of the workload in space on board these satellites. So as these satellites are getting launched, how is all the information coming down to Earth from space? What is the cloud pipeline for Earth observation? As you can see from the image, you get data from sensors. These sensors could be sending data to the satellites. These satellites, which could either be Earth observation remote sensing satellites with cameras, or they could be satellite IoT receivers. They then connect to ground stations, such as what you're seeing here are Azure Orbital ground stations. These are ground stations that are very close to data centers that get the information from satellites directly and send all of this to the Azure data centers. We have over 200 of these data centers worldwide, and we are adding these Azure Orbital ground stations. And once this data gets to the Azure data centers, then we have our orbital analytics pipeline. This is artificial intelligence that runs on this data, giving you insights, turning just data into information, into insights, which are then actionable. For example, you could have these Earth observation satellites capturing images of farms, which are being sent through Azure Orbital to the data centers, where we are then analyzing it, seeing what the crop stress level is, and then sending notifications to farmers. The thing is, even though we are building these end-to-end pipelines and they are operational today, they are not yet real time. Ideally, you want an insight as it happens. As you know there is a disaster happening, you want to know what's happening right now. Imagine wherever you are sitting, you could see how things are in Pakistan right now to help out with the floods that are going on there. That's a big challenge. Currently, from the time an event happens to the time that event is captured by satellites, to the time that is analyzed and an insight is generated, it is a few hours, if not days, before you get all of this data. And this is because of challenges throughout this cloud pipeline for Earth observations. All the way from IoT devices. We are limited with the number of IoT devices that can be supported because of the limited spectrum that is available for IoT devices. So every IoT device is a narrowband device. It takes up, say, 100 or 200 kilohertz of spectrum. So in 1 megahertz of spectrum, you can only have 5 simultaneous IoT devices transmitting at the same time. Given the limited amount of spectrum that is available, you can only support so many sensors simultaneously on the amount of spectrum that is available. For example, if you're monitoring a farm, or maybe say an entire district of farms, the existing IoT spectrum available is not enough to support all the IoT devices. The second challenge is the amount of data that is generated by the satellites. Each of these satellites, especially the ones with cameras, in each pass could be generating over 100 gigabytes of data. You don't have enough bandwidth to send all of this data down to the ground. Another challenge is the amount of available bandwidth to send all of this data from space to the ground. We don't have that much spectrum available, again, from the satellite down to the ground. We also don't have enough of a ground station infrastructure that is available to send all of that data from the satellites to the ground stations. And finally, around analytics. The data, because you can't send all of this data, the AI that you would run, the AI training, would be very slow. Also, we don't get large amounts of data, all the data down to the data centers. So how would you generate all of these insights, given that you have limited amount of data that is available for Earth observation? These are all the challenges that we address through a project that we call Space Connections. Our goal here is to get near real-time insights from anywhere on the planet through all of these satellites, these low Earth orbit satellites that are getting deployed. How do we get there? For each of these challenges, we've come up with solutions. To support limited amount of spectrum for IoT devices, we've come up with a new way to support satellite IoT connections, where these satellite IoT devices can coexist with terrestrial devices, with terrestrial spectrum use. Secondly, for the large amount of data that's generated in space, rather than sending all of them to the ground, we leverage edge compute. Edge compute that you know about, that you could be running on your computer, or you could be running on, say, a 5G base station. We've come up with ways where you could run this edge compute in space on board the satellite. To overcome the challenge of sending large amounts of data from space to the ground without enough of a ground station architecture, we've come up with a new distributed ground station architecture where you have really low-cost ground stations that are distributed that, in conjunction with the expensive high-end ground stations, can significantly reduce the time taken to transfer large amounts of data from space down to the ground. And finally, to enable AI on limited amount of data, we are using federated learning, where instead of running these AI training on the ground in the data centers, you could be running AI training in space. And we've also come up with new ways to do multimodal AI. I will expand on each of these techniques in the rest of this talk. So the first challenge is, how do you scale satellite IoT through spectrum sharing? The challenge here is that the amount of spectrum for satellite IoT is very limited. To overcome that, we've come up with a new way to use databases where every device can then consult with a web service and know, based on where they are, what spectrum and what modulation they can use. Another challenge is that IoT radios are omnidirectional. That is, these satellites, they have antennas that are not beamforming down, but they are omnidirectional antennas. They have a very large footprint of the amount of area that they cover. And the third challenge is that the ground stations or even the sensors are low cost. So you can't really do the high-end processing that you could be doing on these million-dollar ground stations or on devices that are more expensive. So this is just showing what we've observed for a satellite that we launched through Microsoft Research. We launched a satellite for experimental purposes with a company called FOSSASat, which is called MSRSat-1. And through these satellites, we are observing the signal in the time domain. As you can see on the top is what you would have received from MSRSat-1. At the bottom, what you're seeing is you really don't see these packets in the frequency domain. This is because of the amount of interference that we are seeing in these narrowband parts of the spectrum. Another challenge is here, for example, this is not a packet that was actually sent by the satellite, but if you used existing receive pipelines, you would have noticed that, hey, there was a packet there which really did not belong to our satellite. In order to overcome these challenges, we use two approaches. The first is that of a database. Every device would then report its location, would report what spectrum it is using, would report what is the SNR and what is the expected demand, number of packets it needs to send. And based on that, the web service would send a response saying what spectrum can it use, and not just what spectrum can it use, along with that, the power levels and the modulation that it can use at that location. And the second approach we are using to enable satellite IoT radios to coexist with terrestrial radios is that of leveraging the artifacts of satellites, things such as Doppler shift, things such as if we know when it's going to tumble, when it is going to be facing the Earth. We can leverage all of these artifacts to design intelligent systems that can still decode packets even when there is interference. To walk through how this system works, Tushar, who's in my team, he'll talk about how he and WebHub and others in the team have built a system showing the entire coexistence of satellite IoT systems in action.
Hello everyone, this is Tushar working for Microsoft Research at Redmond. In this video, I will demonstrate you our spectrum exploitation technique in action. Let me walk you through our setup first. In the setup, we have a software-defined radio-based ground station. This is our partner ground station located in Europe. Here, the SDR generates raw SDR recording that we further process using our technique for demodulation and decoding. It extracts data packet in bytes from the raw SDR recording. In this demo, we are going to use SDR recording of an event where two satellites were in contact with the ground station, MSRSat-1 and a neighbor satellite from the same constellation. Both satellites were operating at 401.7 MHz using 2 GFSK modulation. We collected recording for 15 minutes, where the contact time was around 7 minutes. Two satellites transmitted total 14 packets during the contact. Now, in our initial inspection of the raw SDR recording, we found most of these packets buried under the noise and heavy interference. This makes the detection and decoding of the packets very challenging. With our novel spectrum exploitation technique, we tackle this challenge from two aspects: interference mitigation and collision resolution. Here, we leverage the satellite artifacts, such as Doppler signature, that embed unique attributes in the RF signal received from each satellite. It enables decoding satellite signal in presence of heavy noise and interference. Now let's see how our technique performs in real world compared to a classic approach. First, we run the classic technique on the raw SDR recording collected from the ground station. Let's see how many packets we can get from the recording. As you can see, we get only 2 packets decoded in bytes out of 14 using the classic technique. Now we run our proposed technique on the same SDR recording, and we want to see how many packets we can decode. We have started getting the packets. As you can see, using our technique, we are able to decode all the 14 packets with 100% success rate. In summary, our spectrum exploitation technique is able to decode all the packets received from 2 satellites in presence of heavy noise and interference, where the classic technique exhibits below 15% success rate. That's all from my side. Thank you all for being with us.
Thank you, Tushar, for the demo. Next, I'll talk about the next part of our system, which is on edge compute. How do we leverage large amounts of data that is generated in satellite and not send them all to the ground? For example, here, what you're seeing is one of those examples where the x-axis is the number of satellites and the y-axis is the number of frames that need to be sent down to that are actually discarded. The amount of data that is wasted with the number of increase in the number of satellites is pretty significant. As you increase the number of satellites, you just can't send all of that data down to the ground. And this problem becomes even more significant for multispectral or hyperspectral data, where you have many more spectrum bands. So the amount of data that you generate is just too large. And further, not all of the data that is captured by the satellites is equally valuable. For example, more than 67% of satellite imagery is cloudy. So you don't really need a lot of data that is cloudy being sent down to the ground. So here, for example, if what you're seeing is on the left, you have a reference image. On the right, you have a captured image. Only certain parts of the captured image are actually needed. So you could get more than 16 times compression if you only sent the parts of the images that were changed. So these are some of the questions that we answer as part of a system where we do edge compute. The first question we answer is, how do you stream all of these images to the satellites? How do you stream the reference image to the satellite so that at the satellite you can compute what are the changes to a pixel level diff and then only send out any of the changes that are there in the images? Streaming a full resolution image is going to be very, very expensive. So instead, what we do is we do downsampling. We don't miss areas that have changed, and we do this very infrequently, as small as once a month, and it works really well with our system. The second key challenge is that of handling dynamics in the system. That is, clouds move. Now, as clouds move, do you look at clouds as something that has changed? Similarly, it's not just clouds. The illumination in the system in each of these images changes as well. The same site imaged multiple times might have different illumination. There are many other dynamics, for example, around images, around sensor noise, and so on. And this is something that we need to adjust as part of our system. This is what our end-to-end system looks like, all the way from the observed pipeline. What we are doing here is, this figure shows the various steps that are involved in our edge in space approach for compression. First, we remove clouds by using detecting and filtering the clouds. We use cheap decision tree-based cloud filtering on 16 times downsampled images. After we've done the cloud filtering, we adjust for illumination, which is again one of those inexpensive algorithms that we used. And then we do a pixel-wise change detection. And if it's unsure if it's changed or not, we always mark it as changed. And then, only then do we encode the images and send down only the changes in the system. Using all of these approaches, we get up to 5 times compression in using edge compute in space. So next, Shadi and my team, she'll talk about some of the work that we have been doing along with Kuntai and Brad at CMU on incorporating this edge-based compression system, and she'll show you the entire system in action and a demo of our edge in space system. Shadi?
Now let's take a look at a demo of the compression in space work. Here we're comparing a captured image of an area against a historical image. These are both from the Sentinel-2 datasets, where the historical reference image is from end of July 2020 and the new image is from September 2020. So if we start running the code, as you can see, first we load the new image, we downsample it, remove any clouds from the image, align the illumination, and then finally detect changes and encode those changes. Let's look at the visualization of these different steps. So first, this is the input image and the reference image for the same area around like 2 months apart. As you can see, the images generally look very similar except for some changes in the agricultural areas. So as the first step, we remove clouds, which we use decision trees, small versions, specialized versions for this step. In this case, there were no clouds to be removed, so there are no changes on the image. Then we align the illumination for the 2 different images, and this is before illumination and after illumination alignment, which we use a linear regression model for that. And then finally, we do a pixel-to-pixel comparison of the 2 images, which you can see the changed areas detected. They're mostly, again, on those agricultural areas and a very small portion of the overall image. And finally, we use the current state-of-the-art JPEG 2000 approach to encode just the changed areas, which are marked and highlighted, and those would be the only areas that we download and use the historical reference on Earth to compose the rest of the image. Now let's take a look at the end-to-end demo of what is the impact of all of these steps and how much savings do we get. So we compare our approach, which is the one on the left, with 2 other baselines. The one on the rightmost is JPEG, which is the current state of the art done for processing and compressing images in space. And then the one in the middle is if you use edge computing but only do cloud removal when doing edge computing. So here, as you can see, our approach quickly identifies the areas of change and only downloads those areas, while both two other approaches take quite a while and need to download quite a lot of data. And we also look at cases where there are more clouds. So here you can see the same area captured, but on a much more cloudy day, and compare it against the same two baselines. As shown again, we do get benefits and are faster, especially compared to the state-of-the-art current JPEG approach. Our improvements are slightly worse than cases when there are less clouds, but there's still substantial benefits from. Here we compare our approach over a large geographical area and over a 1-month period. So we take 1,200 by 100-kilometer areas, and we monitor them over a month. That means that there will be clouds and non-clouds over that period. And we compare our approach, which is Earth plus JPEG, with the two baselines we just discussed, the JPEG currently done and JPEG with cloud filtering added in space. On the graph here, on the x-axis, we have the file size for different approaches, which lower is better, and the y-axis is the PSNR, showing how well or how much the compression impacted and how much noise it added. So higher is better. As you can see, we get substantial compression, and on average, we get 5x better and reduced file sizes using Earth plus JPEG.
Thank you, Shadi. The third challenge, as I had talked about, is how do you send all of this data from space to the ground, given that the amount of ground stations is very limited? To address that problem, we've come up with a new approach called distributed ground stations. So the challenge that we face is the following. That is, suppose you have a ground station and satellites. In every pass, the satellite could be generating over 100 gigabytes of data. And all of this data needs to be sent down, even though the satellite is in contact of the ground station for only about 10 minutes. So in 10 minutes, how do you send all of this data to the ground? And the amount of data that is being generated is increasing based on the resolution of the cameras, based on the amount of spectrum that is captured, like for example, if it uses multispectral or hyperspectral imagery. So how do we get all of this data down to the ground? Today, the way the system works is you would deploy these really large, complex ground stations, which are multi-million dollars, and you have about 4 to 5 of these located in different, around close to the poles, because these satellites mostly have polar orbits. However, a challenge of this system is that it becomes very expensive, but in addition to that, it's also very high latency. That is, you would have a long time before all of this data is sent down from the satellites down to the ground stations. And another challenge, of course, is failures. For example, if any of these ground stations go down, then it becomes very disruptive to the entire end-to-end system. So our proposal, this was published in last year's ACM SIGCOMM, is that of a distributed hybrid ground station approach. This work was done with Deepak Vashisht, who's now a professor at University of Illinois. He was then in my team. He was part of the networking group at Microsoft Research, and Jayan Shenoy, who's a student of Deepak's. So our system, the way it works is the following. We have our proposal involves these low-cost ground stations. You can think of these Raspberry Pi-based systems, which are distributed geographically, and they are mostly receive-only. They are not sending anything up. These are just receive-only satellites. Imagine people just mounting these on top of their buildings as receive-only devices, like people mount their dish antennas or satellite TV antennas. So the question then we ask is, can a network of these tiny ground stations outperform a capital-heavy, very huge ground station architecture system? A proposed system is that to augment the existing high capital intensive system with a few of these expensive ground stations with lots and lots of low cost ground stations. This system is going to be fault tolerant, it has low latency, and it is hybrid. That is, it coexists so that not every ground station needs to transmit. The system, if it could be made to work, would significantly outperform the system. But to make it work is challenging. The first problem is that of rate adaptation. The problem here is, what is the data rate to use when sending data from satellite to the ground receiver, this low-cost ground receiver? Typically, rate adaptation systems require feedback, require information from the receiver about what is the SNR. And without this information, how do we estimate what is the modulation that should be used? The way we solve this problem is using link quality estimation. We predict the distance using orbital parameters. We use weather forecasts for weather loss. And then we use a machine learning algorithm to train for multipath and for hardware losses. We combine all of these things to predict what is the data rate that should be used for that particular link from the satellite to the low-cost ground station. The second challenge we had to address was, how do you schedule the satellite versus the ground station links? That is, there could be many ground stations that could be active. Which one should be activated at any instant in time? And the key goal is, how do you do this so that you're trying to optimize for low latency, high throughput, while ensuring that you're keeping track of geographic restrictions? If you look at it, this corresponds to a bipartite graph matching problem. However, and the switching links takes time, and matchings are not really time dependent. So then this problem becomes very quickly NP hard. So how do you solve it? We use an approximation algorithm, a greedy algorithm, but this greedy algorithm has a penalty associated with it if you make the wrong decision. And with this system, we have actually shown that this system can lead to up to significantly improve the total time of downloads from space down to the ground. A third challenge that we had to address to make this low-cost ground station system to work was that of lack of acknowledgements. That is, because your ground stations cannot transmit, they are receive-only ground stations. They cannot send acknowledgements. If they cannot send acknowledgements, how does the satellite know that the ground station has actually received the packets that it has sent? To address this problem, so for example, the challenge here is, you have this, the way we do it is using lazy acts sent by transmitters. That is, your acknowledgement is not sent immediately, but sent in a delayed manner by a satellite that can actually communicate, by a ground station that can communicate to the satellite. So for example, in this case, as you can see in this example, the satellite receives the acknowledgement from this transmit capable ground station. As the satellite goes around, we have the complete system, the distributed ground station in action. As the TX capable device sends the acknowledgement, the satellite, as it goes around, when it comes in range of a tiny ground station, it sends a packet down. Similarly, when it gets to the next one, it sends a packet down as well. And it keeps doing it as it orbits around the Earth. We have evaluated the system at scale with the SatNOG system. We use the data from the SatNOG's deployment with 259 satellites, 173 ground stations all over the globe, as you can see in the slide. We are generating over 100 gigabytes of data per day per satellite. That's about 26 terabytes total. And the baseline here is, we start with 5 expensive ground stations, and then we include all the others, 173 ground stations. Our system gets at least 10x higher median throughput than existing systems. In the paper, we discussed the system in detail, but at a high level, if you look at this slide, here what we are comparing is the latency. This is a CDF for 3 different approaches. We are looking at a baseline system, which is what you would use with 5 ground stations, a DGS deployment where you have all of these ground stations acting as distributed low-cost ground stations, and the dotted line, which would be about, if we only pick 25% of the ground stations as the distributed ground stations. As you're seeing in the system here, this leads to a latency from an hour to minutes if you start using the distributed ground station architecture. So now I've talked about 3 of the 4 innovations that we've come up with. And the last question we asked was federated learning around how do we do AI in space? That is, without sending all of that data from space to the ground, how do you still come up with insights on top of this data? The key technology for real-time space applications such as real-time disaster monitoring and so on is AI. Most of these AI models today rely on satellite data being downloaded to the ground. But as we've already seen, downloading all of this data to the ground is increasingly difficult due to the limited downlink bandwidth and limited ground stations, as well as all the issues with regulations. So the key opportunity we have in this work was we looked at how do you train all of these AI models in space without downloading all of the data to the ground. The opportunity here is to leverage federated learning methods to achieve this objective. In particular, the satellites train these local AI models based on locally collected data, and the ground stations then, on the other hand, iteratively collect and update the global model based on this local model. However, it is fundamentally challenging to apply existing federated learning methods in this environment because of 2 reasons. One, the connectivity from the satellites are sparse, and these are heterogeneous. For example, you can see that issue with these federated learning solutions in this particular slide, around idleness, that is the satellites with limited amount of connectivity, they work as stragglers. And the other problem is that of staleness, that is gradients are based on outdated global models, which can lead to an unstable AI training. These are the challenges that we address through our innovation with FedSpace. FedSpace is an algorithm that is designed to run efficient federated learning in space. The key idea of FedSpace is that satellite connectivity is time varying, but it is also at the same time deterministic and known. That is, given an aggregation schedule, the ground station can then calculate the distribution of staleness among the different local models. Hence, what we do is we formulate this as an optimization problem to find the aggregation schedule that maximizes the utility function that you're seeing on this slide. This was work that was led by Kevin in my team, who along with Jin Hyun from USC and with Chenning who's now at MIT. And this paper has been published and it's put in archive. Please do read and give us feedback about the use of this new system, which we call FedSpace. In addition to doing AI training in space, the other challenge that we are looking at is how do you generate insights from all of this data that is coming from all over the planet? In order to do that, we've innovated on new techniques for multimodal AI, which we are calling Project Terabytes. We collect data from a variety of data sources coming from, say, the FarmBeat system or planetary computer or sensors that are all over the planet. On top of that, what we're building is firstly a data store. And in addition to a data store, we're also putting a compute layer. And together, we are making all of these capabilities available to the community. That is, we build a layer on top through which either using a Power Client or through Python SDK client, we're building these SDKs where any user can come and look at all of that data that is available, geospatial data from satellites, from different types of satellites, from sensor data, and then being able to combine these different data streams to come up with new insights on geospatial data. Just to give an example, suppose you want to know what is the soil moisture map for a particular farm in, say, Eastern Washington right now. The way you would do it is you would look at the sensor data that is coming in, you would look at the satellite data that is coming in at the same time, and then based on the sensor data and the satellite imagery, you would combine them to then build out a soil moisture heat map so that within minutes, you know what's happening in another part of the world. There is a forest fire going on. You can look at weather station data. You could look at, again, satellite data. You can estimate how that forest fire is going to spread in near real time with the end-to-end system that we built. As part of this Teravibe system, which we have made open source and is available for the community as of September, you'll be able to then use this system to then build your AI capabilities. And as part of this stack, we are including a lot of innovations from Microsoft Research. One of those innovations that we are including as part of the system is called SpaceEye. Previously, I mentioned how over close to 70% of the satellite imagery is cloudy. If 70% of the imagery is cloudy, you really can't see anything that's happening below the clouds. One of the new systems that we built, this was done by Peter Olson in my team and Ming Min, who's now a professor at UPenn. Back then he was a grad student at MIT. What we did here was we looked at another satellite which has synthetic aperture radar in it. As you know, radar signals, they go through clouds and they reflect differently from different surfaces. Based on this reflection, we then came up with a new technique called partial observation GAN along with neural attention, where we are then able to predict what's happening below the clouds in satellite imagery. Like here on the left are the images you would get right now. If you looked at satellite imagery, on the right is using SpaceEye, the images that we are able to predict. You can see below the clouds when a farm is tilled, when did emergence happen, when did irrigation happen, all of these events as they are happening. This is just one of the AI components as part of TerraVibes, but we are building many more to enable multimodal AI to generate insights on satellite data. So to conclude, as part of today's talk, I've talked about this really exciting project that we are doing as part of our team called Space Connections, where we are collecting data from a variety of data sources and working on ways to reduce the time from the time a data is collected to the time the data is transported to the cloud, as well as from the time a data is generated to the time you can extract insights on top of all of this data, transforming all of the data in the planet to information and insights. Please do reach out to us if you wish to learn more or to collaborate with us on any part of the system, be it on IoT, be it on edge in space, ground station architectures, or the cloud and the AI architecture around it as well. Thank you.